Hey guys, today we're going to be discussing a couple of properties of gases known as diffusion and effusion. So let's go ahead and start by defining what diffusion and effusion are. So the first one I want to define is effusion. Now effusion is going to be when a gas is going to escape from a small hole punctured into a container. So if I take a balloon and I pop the balloon, but it doesn't rupture, it just has a hole in it, the gas is going to leak out. That process of leaking out is called effusion. So when gas seeps out through a hole, it's going to effuse. Diffusion, on the other hand, is when a gas is going to move within an uncontained area. You might remember diffusion as being discussed in biology as the diffusion through a membrane, but in some cases, that's actually not always going to be utilized in the same context. So for instance, in chemistry, if I have a candle burning in front of me, let's say it's a cinnamon-scented candle, as I move away from the candle, I can still smell it. And the reason I can still smell the candle is because as the candle burns, it releases volatile chemicals into the air as gases. Those gases, because of the fact that the molecules are moving, begin to move away from the point source of the scent, of the odor, the candle. So as they move away from the candle, I can still smell them because they still exist. That process is diffusion. So diffusion and effusion are both very similarly related because they both involve the movement of gases. The difference in the two is that effusion is through a hole, whereas diffusion is just kind of in an open space. In both cases, we're talking about the movement of molecules from an area of higher concentration to an area of lower concentration. The reason for that is probability. So it's all about probability, which means it has to do with the number of molecules, the pressure, the temperature, all of these variables that we've already discussed. We now need to think about how they affect both diffusion and effusion. Specifically, we're focusing here on temperature. Temperature matters the most because we normally control for the other variables. So let's focus in this video on how temperature impacts the rate of diffusion and the rate of effusion. Now the way these are all interrelated is through a single equation. Kinetic energy of a molecule is equal to 1/2 the mass of the molecule times the velocity of the molecule squared. Now temperature is how we measure average kinetic energy. So if we look at the temperature of a gas, what we're seeing is not the kinetic energy of every molecule, but simply the average kinetic energy of all of the molecules present. That's because molecules are going to be colliding with both each other and the wall of the container. And if I put a thermometer in it, they collide with the thermometer. And that's what actually creates the energy to raise the temperature of the thermometer to be read. So all of this process is through the collision of molecules and the movement of molecules. Well, the movement, that's their velocity. So as molecules move faster, they are going to exert more of a force during any collision. So higher kinetic energy of the same gas represents a greater velocity of movement. So as the kinetic energy, i.e. temperature, increases, so does the velocity. Now let me introduce you to a graph that's going to play a huge role in this unit, but also in the rest of chemistry this year. This is called the Maxwell-Boltzmann curve, or oftentimes I just shorten it to Boltzmann curve. Now the Maxwell-Boltzmann curve is going to represent how a sample of molecules is going to exist in terms of their kinetic energies, or velocities in some cases. Now if we look at the Boltzmann curve in front of us here, what you'll see is that it's not a normal distribution. So it's skewed. There are more molecules with lower energy than there are with higher energy. Now it's going to be important in the future. The shape of the curve really does matter. As you get higher and higher energies, some molecules are going to have greater energy than the average, and some are going to have less energy than the average. But when we measure temperature, we're simply measuring the average. So if we look at the changing temperature, each time we increase the temperature, the average of this curve shifts to the right. But because we're looking at the same number of molecules, as we shift to the right, it also gets a little bit shorter because we're moving the entire thing to the right. So one critical factor here is you have to understand that the Boltzmann curve is of a set number of molecules. Because of that, as you shift it to the right, you have to decrease the amplitude, so reducing the height of the curve. In addition to kinetic energy, a Boltzmann curve can be used to predict the velocity of a molecule. And that's because velocity and kinetic energy are very much related. Remember, kinetic energy is 1/2 mass times velocity squared. Now there's this thing called root mean square speed. You don't really have to know about that directly, but we can think of root mean square speed as it pertains to velocity. Velocity of a molecule is going to be impacted by two things. Number one, the temperature, i.e. kinetic energy of that molecule. Secondly, it's going to be impacted by the mass of that molecule. The bigger a molecule is, the slower it's going to move. Okay, and that's because if we're looking at two molecules of the same temperature, they have the same average kinetic energy. In order for the kinetic energy to be the same, again, 1/2 mass times velocity squared, if your mass goes down, your velocity goes up. If your mass goes up, your velocity goes down. So let's do an example where we're going to apply this law of diffusion or effusion to a real-world scenario. Let's say I've got two samples of gas on two sides of a container. I'm going to release each simultaneously. One of the samples is nitrogen, N2, and one's chlorine, Cl2. Now, in both circumstances, the gas is going to diffuse in every direction. But if we're going to target this towards the middle of the container, I just want to know which one's going to reach the middle first. Let's say they start equal distances to both sides. If I'm going to do this, I need to know what their relative velocities are, because the one that's going to reach the middle first is the one with the greater velocity. That means I need to know their molar masses. Because they're at the same temperature, kinetic energy is the same. So if kinetic energy is the same, then it's 1/2 mass times velocity squared. The molar mass of chlorine gas, Cl2, is greater than that of nitrogen, N2, right? Which means that the chlorine, as its mass goes up, velocity comes down. So the nitrogen is actually going to reach the center of the container first because it weighs less and therefore is going to diffuse faster. Now in the second problem, I'm going to want to see how we can augment a Boltzmann curve. So we have a curve in front of us, and what you can see is that we have two different shapes. What would have caused the shift from the first curve, the blue one, to the second curve, the orange one? Now, one thing that would have caused this shift, because again, we have to look at the axes. On the x-axis, we have kinetic energy. Kinetic energy is temperature. So as we go from the first curve, the blue one, to the second curve, the orange one, simply increasing the temperature would result in that shift. So that wraps up today's video. Today we discussed diffusion and effusion as properties of gases. Remember, these properties are centered around the kinetic energy equals 1/2 mass times velocity squared equation that's on your formula sheet. And I want to make sure you're, again, aware of how Boltzmann curves can be used to represent the average kinetic energy of molecules and how they can be augmented if you're changing the molar mass and or the temperature of a sample. I'd like to thank Mayuri Venkatesh and Ananya Manglik for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.